Um, what I would like to talk about is something that in Trilogue Studio we are trying to bring sustainable design into the main frame of the design process itself. The reason being that actually what I would like to do is expand the dialogue that we are doing on steel building to actually bring in a little bit focus on sustainability, on energy efficiency. Because steel buildings per se have a higher embodied energy than perhaps say a brick or concrete building by almost about 20%. So right away, we are actually creating a building that is not as energy efficient or as sustainable as we would like it to be. And today, the construction and building industry accounts for about 38% of carbon emissions. And almost more than 50% of this can be actually attributed to steel buildings. Now, so that's why we would like to put design and construction at the heart of climate change action. And it's appropriate to look at steel buildings as they constitute a major portion of the building and construction industry today. What are the current challenges actually? One, I already mentioned that steel buildings have a higher embodied energy. The second is that energy efficiency even today with all of the, India's climate change promises of reducing carbon emissions by 30 to 35% of the 2005 levels by 2030. With all of those assurances as well, it's still energy efficiency is still not in the mainstream, right? It almost comes almost as an afterthought for almost 50, 60% of the buildings that we do. They also lack a cost-benefit analysis because for every a unit of power saved, you are actually investing a little bit delta into bringing about those energy changes, right? So the other thing is they're not comprehensive enough. We should not only look at the steel buildings, you should not only look at the envelope, we need to look at daylight, we need to look at water consumption, we need to look at power, and many other related disciplines. The last, of course, is that there's a bountiful, even in the morning, we heard almost two of the three keynote speakers speaking about the technology that is available to us to actually analyze not just the construction process itself, but also analyze the carbon emissions or the embodied energy. So these are the current challenges that we are looking at as far as steel buildings is concerned, and these are the challenges that we have to actually address. Right? So that's so in this case study, we look at BIM, we are looking at IELS, we're looking at Lumion, and then applying those to water, power, heat gain, and daylight studies. So the project that we are talking about is a battery recycling plant. So imagine it is actually a highly polluting industry. The battery recycling plant is coming up in Cheyyar in Tamil Nadu. The client is Hamaraja Batteries. The site is about 50 acres, and the main built-up area is about 7.5 lakh square feet. There's almost about close to 3,000 metric tons of steel that is actually being used here. So the main plant itself is a T-shaped structure. The number that you see is 07. There are amenities on the southwestern side of the building itself, of the site. And on the northern side, we are actually creating a large urban forest. We are having a water recycling and a water storage tank on the southern edge of the campus that you see in slightly blue-green. And then there are a lot of these surrounding ancillaries. This is almost consuming about, we are actually putting up a substation, 33 kVA substation, because that is the level of power consumption that this industry is actually going to be using. So that's on the, on the south, on the western side of the thing that you see the number 02. So these are all the components that we are actually looking at for this project, right? So, these are perspective views. The project is just started construction. Design is almost complete. Right now, we are actually looking at all the cost-benefit analysis of the sustainable measures that we have suggested for this project. These are just close-ups of the project. The urban forest that we see is at the far end of the campus. which is also, the low-lying areas of this site are where the forest is. There is also on the right side where the rainwater harvesting pond and recycling pond is. Again, close-up shots. These are early stages of construction where we are looking at. It is a multiple, again, the T-shaped structure that we spoke about is almost a 55 meter span with a central row of columns. There are multiple heights of the buildings. It's 17 meters at the eaves. It goes up all the way up to 20 meters. And then there are 3 levels of heights that we are looking at with a perimeter wall of about a meter and a half, and then sheeting above that. So these were all the envelope, the roof, the ventilation that is required for the structure. These were all part of our analysis that we wanted to bring in for the project. So the first, we looked at the wall alternatives. A lot of this is actually plain vanilla, as they call it, like very, very simple first principles. But the idea is that we actually create a template that we can actually use for other projects. It can actually be, shared with the building community, shared with the design community. I also teach at colleges, the thesis. So it is actually a template which we would like to, expand and use for all buildings that as much as possible. Because again, our interest, our passion is to bring sustainability into the main focus of design and construction process. So we start with absolutely the basics. We look at the wall alternatives. We look at a base case scenario, which is just absolutely the steel construction with a galvalume sheet, and then we start adding insulation and then bringing down the U value. And then we don't stop right there. What you see on the right-hand side of the screen is we look at a higher performance glazing, and also we look at a better lighting LPD or lighting power density. So using this as the base case scenario, we then start looking at our analysis to see what is the energy usage intensity. So if you look at on the left side, you have about 480 kilowatt per square meter of energy usage, which is the base case scenario. And then if we were to add insulation to it, we start beginning to reduce the energy usage by almost about 80 kilowatt per meter square. Now this, if you compare with regular brick and mortar or even buildings made of with fly ash or hollow block, or even RCC buildings with insulation, this energy usage is almost about 25–30% higher in steel buildings. So already you are starting at a disadvantage as far as sustainability is concerned. So what we can only do is bring down the effect or reduce the the negative effect on the environment. Then we expand the dialogue, we take it to the roof. And when we look at the roof, the base case again is an uninsulated galvalume sheet. Then we look at what is the U value of that. We analyze different insulation options, which could be XPS, extruded polystyrene. We look at puff, we look at polynume. And again, each of these suggestions has a delta X, which will be an additional investment that the client will have to make. But what we essentially look at in the end is the payback period. So if I were to reduce the energy ingress, we are automatically reducing the mechanical ventilation. We are looking at a better lighting for the project as well. So end of the day, it is like the payback cycle is very important. And if we are able to establish to the customer that the payback period for any measures that we adopt is about 5 years, 3 years, 4 years, we have a better chance of convincing customers to adopt energy efficient measures. So with each reduction, with each additional energy efficient or a material change or a material suggestion, we start bringing down the U values of the project, U values of the wall and the roof assembly. So once we looked at the energy usage, we went from 480, we brought it down to about 400, and then we start reducing, and with a better quality of insulation in the project, we actually bring it down by almost about 150 or 160 kilowatt per meter squared as far as the energy usage is concerned. Now, we don't stop right there. We expand. Again, I'm telling you, we are building on layers and layers of sustainability into the project. We then look at light power density. And by using better quality, today LED is actually it's almost, there's nothing very special about using LEDs today. Everything is today, people talk about LEDs. But LEDs itself come in many, many different varieties. They have a better light power density depending on what choices you make. And with better LPDs, we actually start reducing the watts per square meter that we consume. We go from 10.23 whatever watts per square meter all the way down to 5.1. Now, I'm neither an electrical engineer nor am I a daylight specialist. I'm an architect with an interest in sustainability, and my single focus is to be a facilitator, to bring experts from different fields and coordinate everything together, so at the end of the day we get an environmentally responsible building. So as we go forward, as you reduce the light power density, your total, only looking at the changes in the light power density, we reduce by about 25, 30 kilowatt per meter squared. But when you combine it along with adding all the proposed case, we're looking at the sheeting, we're looking at the insulation, we're looking at better quality glazing, and we're looking at light power density, we finally end up coming from 480 kilowatt per meter squared all the way down to 199. So there is a lot of data out there that we can actually analyze and then suggest a design that is actually very environmentally responsible. It is very possible. Now, we then move to mechanical ventilation. If you see, the entire building is split into 5 bays, and these are the literally the heat gain from the equipment that we are looking at, to 20,000 all the way up kilocalories per hour. And then they need, for the ventilation of that, these are the data that is available for us in terms of the provision of louvers. Now, we cannot provide all of those, this cannot be just by natural ventilation. We have to provide mechanical ventilation because the shortfall in the louver sizes or the opening sizes is very evident if you want to go for natural ventilation. So what we do is then we compute what is the equipment selection for providing that mechanical ventilation and what is the power requirement for that particular equipment with the capital cost. And we then say that if we can generate renewable energy on the site to power this mechanical ventilation, then again, it is a win-win for both the customer as well as for the users of the plant. And then that will have a payback period of 6 years. Yes, our ideal situation is if the payback period is below 5 years. But in this case, considering the size of the plant, we are still doing okay. So if you look at the power consumption cost versus we saw on the earlier slide, the capital cost of solar panels is about 9.75 crores. Then we're looking at about six years in which we can get a payback. The last, of course, is looking at daylight. And we did an analysis using IELS for the summer solstice and the winter solstice. And what is the shading of the building at both of these? Of course, we do it even for the equinox, both the summer and the winter equinox, but I'm just showing you the summer and the winter solstice. And we then look at what is the daylight that is available to us for a base case scenario. And if you look at it, I'll just go only to the summary. Again, a lot of software is available out there. I'm sure all of you are aware of it. But the effective daylight with the base case scenario is only about 37%. Now, if I were to, that is actually not as per ECBC codes, as also by conventional standards, it should be at least be 50%. When I say effective daylight, that means at least 50% of the floor space should have more than 2,200 lux. So we are falling short. It's only 37%. So what do? We go back in and increase the window wall ratio with a higher solar heat gain coefficient, because if you can't keep creating larger openings because that's going to bring in more heat. So we look at larger openings with a better solar heat gain coefficient. And once we do that and we reanalyze it, what we end up seeing is almost that we get we look at almost 98% of the floor space has a higher daylight of 2200 lux. Now what does it do is that it automatically cuts out the dependence on artificial light, which automatically improves the light power density within the plant, which automatically goes back and improves the the energy usage intensity. So it is all very intertwined, it's all very interlinked. So that is what is important for us to understand. The last part is the water balance. Water is actually very, very important component of this plant, as also many facilities. Again, we look at 3 stages of recycling. When we are looking at 3 stages of recycling, a very, very high water consumption is there. There is almost about 294 KLD of water is required for the process. And through recycling, we are able to actually bring the net reduction is almost 128 KLD is possible by this 3-stage reduction, 3-stage recycling. We also, and during the monsoon months, you saw in the perspective, there was a large water storage and water recycling plant. We are able to, with a peak runoff saving, with a peak storage of 30 minutes water storage for during stormwater, during the monsoon months, we can add about 1400 KLD of water storage is possible to be stored, and thereby that again reduces the total dependence on municipal and groundwater. So that's what we've been attempting, and that's what we are trying to look at, building projects in a holistic manner, whether it be steel, whether it be concrete. We do a lot of steel buildings. Actually, steel buildings, honestly, is the bread and butter of construction industries, architects, et cetera, no matter what you say. So steel buildings have a significant, can make a significant contribution to climate change, and that's what we are attempting to do. Thank you very much.